All right. Good morning, good afternoon, good evening, depending upon where you're joining us from. My name is Damon Hernandez. I'm going to be your host today for our WebGL Meetup, where we're coming straight out of WebGPU. So today's going to be a fun day where we'll be covering all things WebGPU related. And to kick us off, as always, we're going to get our update from the Mr. Ken Russell, who is our WebGL co-chair or chair, forgive me, followed up by Kai, who's going to share with us what's going on with WebGPU, followed by Marcus and Ian, who are going to show us some very cool applications. So with that, Mr. Ken, the floor is yours.
Super. Thank you, Damon. Hello, everybody. Let's get these slides presented. Okay, how's that coming through?
Perfect.
Okay, super. So welcome everybody to the WebGL WebGPU. I should have stuck a WebGPU logo on the slide. Meetup for May 2021. Let's just dive right in and get started. So a brief agenda today. I cut out some of the duplicated agenda items from last time. If you are interested in status updates on those, you can go back and look at the slides from the previous March meetup, but not a ton of concrete progress has been made in those areas. So I decided to go for a shorter update this time. So, but to mention, there is a ton of cool stuff that comes out in the 3D on the web community all the time. And we, as the WebGL working group, try to find these and highlight them to the community. They're sent by email every couple of weeks to the WebGL developers list. They're also archived on a blog. Please do join the community and share your own creations and findings. I know that there's a ton of you out there that are developing awesome stuff. We'd love to hear about it, love to hear your feature requests, issues that you're seeing with the API or implementations. We want to make it work as well as we can for you. So please come and participate. One of the big news items for the past several months has been WebGL 2 and Safari. And so a couple of updates here. The latest code here can be tested on both Mac and iOS. You can download the Safari Technology Preview. On iOS, it is definitely available both in iOS 14 and the betas. You can turn on WebGL 2 in the Safari settings and it works. It's our latest code up there in WebKit, but sometimes it's a snapshot from several months old. You can look for the X color buffer half float extension on the WebGL report website to confirm whether you're getting the most recent code. I'm quite sure that the iOS betas do in fact have the newest code or close to it. Now, unfortunately, this isn't turned on by default yet, but we're continuing to encourage Apple to do so. It is totally safe, by the way, to browse the web with WebGL 2 turned on in the Safari advanced settings. It's fully validated, so no worries there. There are great collaborations still ongoing in this area. Apple has just turned on Angle's Metal backend in Safari Technology Preview revision 124, and they're continuing to make major improvements in that area toward full compatibility. You can follow progress of the project on the issue tracker, and basically you can rely on availability of WebGL 2 everywhere very soon. So do invest the time to upgrade your applications now, test WebGL 2 in Safari, and file any bugs that you see on WebKit's issue tracker, and we'll collectively take a look. One substantial piece of progress from the working group is that there's been recent consensus for how to expose the base vertex and base instance functionality, including in multi-draw form. This particular piece of API functionality improves geometry batching by better allowing multiple models vertices to be put in the same buffer object. So you can watch for these in upcoming posts to the public WebGL and WebGL dev list. And there are a few potential use cases linked here. These slides will be published very soon after the meetup, so don't worry about scribbling down URLs, but you'll be able to click these and go there directly. So WebGPU status. The spec and implementations are moving along well. We are collectively trying to expand out the conformance test suite so we can make sure that the implementations are portable across operating systems and browsers. The implementations are all behind flags in browsers right now. Don't browse the open web with them turned on just yet, because the kind of validation that's there for WebGL isn't really fully present for WebGPU yet, but it's getting there. And WebGPU is going to be the place where you get compute shaders on the web. They're awesome, they work, and want to encourage you to start playing with it now and seeing what you can do. Kai Ninomiya, following me, is going to give a great presentation on what the API does, what you can do with it, and so I'm looking forward to that and hope you all are too. With that, we have a great group of presenters today. Kai will give an intro to WebGPU. Markus Schütz from University of Vienna will give a great talk on point cloud rendering with Poetry. And Ian Keogh from HighPar will give a talk on generative design as it relates to architecture. And we'll answer your Q&A live at the end of the session. Please feel free to type your questions into the Q&A panel at the bottom of your screen. And that's it for me. Thank you very much. And I'll hand it back to Damon.
Awesome. Thanks so much, Ken. And thanks for saying about the questions. So make sure, folks, to type in your questions in the Q&A in the bottom. And up next, we have Kai. So Kai, if you just want to grab the screen.
All right. One second. All right.
We see your screen and we
cool.
see it in presentation mode. You're good to go.
Great. And do you see me?
Yes, we do see you.
Awesome. Hey, everyone. I'm Kai. I'm one of the editors for the WebGPU specification at the W3C, and I'm a software engineer in Chrome. My pronouns are he or they. And today I'll be giving an intro to WebGPU. So what is WebGPU? It can be thought of as a successor to WebGL. Of course, WebGL is not going anywhere. We just got a great update from Ken on the current status of that. And WebGL is still going to have somewhat wider reach because the hardware requirements of WebGPU are quite a bit higher. So a lot of older devices, especially older mobile devices, for the time being won't be able to support WebGPU. WebGPU is a new explicit style graphics API. So you may have heard of Vulkan, Metal, Direct3D 12. These are all moving. These APIs are all moving the design in a direction that achieves higher performance and extracts more performance from the GPU. And it gives a really much more solid foundation to expose all those shiny new hardware features that everyone wants to use. WebGPU has a new shading language, WGSL, which we pronounce as WGSL. It's designed for WebGPU and the web. And its semantics are based on all the existing shading languages that it needs to run on top of. So of course, the burning question on everyone's mind is, when are we going to get WebGPU? So I'll try to give an estimate. We're expecting a 1.0 spec around late this year. And hopefully we'll be able to ship implementations somewhere around the same time. Right now, there are preliminary unsafe implementations in Chrome and Firefox. So you can check out the implementation status at this URL. But you can go enable flags in Chrome Canary and Dev and Firefox Nightly, and that will enable WebGPU in the browser. These two implementations are not quite interoperable yet, but we're approaching interoperability, so things are going pretty well. There are a lot of demos that actually can run in both now. On top of this, Chrome is planning a pre-1.0 origin trial, hopefully targeting this around September. And this will allow websites to opt into use of WebGPU, of a pre-release version of WebGPU on public websites on users' machines. So this will be opt-in, and you'll be opting into potential API breakage, because we might change the shape of the API between that origin trial and the time that we release 1.0. So just a couple of the new features, exciting new features that WebGPU will bring. Of course, compute shaders, but there's also some really important things for performance, like pipeline state objects and render passes. And then in the future, hopefully post 1.0, we're expecting, in the very near future after 1.0, we're expecting to see multi-threading support, so ability to use WebGPU, a single WebGPU device from multiple JavaScript threads at the same time. as well as like more shader features like float 16 and subgroup operations and things like that. And of course, in the future, there are many more possibilities, including the ever exciting mesh shaders and ray tracing. People have already started investigating adding ray tracing to WebGPU. It's a big task, and to some extent, we're waiting to get more adoption across the hardware ecosystem, so that this functionality will actually be useful to end users. Of course, everyone always asks, why not a Web Vulkan? So of course, WebGL was developed in Khronos as essentially a port of bindings of OpenGL to OpenGL ES into the web. There are a lot of reasons that we didn't go with a Web Vulkan. So one is security. Vulkan by design is a C-like API. It's hard to validate. Any misuse of the Vulkan API can result in undefined behaviors. And of course, we can't have that on the web. So we'd have to sort of design around all those corners to make sure that there's none of this, no security issues. Another thing is asynchronicity. So in browser architectures, untrusted web content runs in separate processes and strictly sandbox processes that don't have any access to system hardware or the disk or things like that. Of course, the GPU drivers need to access to the hardware, so they can't run in those sandbox processes. So we run the GPU drivers in a separate process, and we need to do sort of inter-process communication between the content process and the GPU process in order to run WebGPU content. And of course, we do this today for WebGL as well. But by design, Vulkan is hard to fit into that model. On top of that, the JavaScript runtime is asynchronous. So async is a first-class concept in JavaScript, whereas things like threads, which are first-class in native languages, are much more heavy-handed. And then the last thing, the most important thing really, is portability and portable performance. So Vulkan, of course, gives you extreme control, gives application extreme control over what happens on the hardware. But apps really have to adapt to the hardware in order to run and to run well. So there are a lot of there's a lot of hardware geometry that will be exposed to the application, and it has to adapt to that. And developers have to optimize for different hardware to make sure that they're getting optimal performance. WebGPU, on the other hand, is write once, run anywhere by default. So if you don't opt into, like WebGL, if you don't opt into any additional features, then the features that you'll get will be the baseline that's available on all hardware. And we even go a little bit farther than WebGL, and we apply the limits. We apply this philosophy to the limits as well. So you won't be able to exceed, say the maximum texture size without explicitly opting into that. And that'll just make sure that any code that you write is almost certainly going to run pretty well on a mobile device, for example. As an aside, WebGPU is also useful in native and WebAssembly. So it's designed for JavaScript first, of course, but it's fundamentally just a hardware abstraction layer over Vulkan and Metal and Direct3D12. So we can get that same portability, that same write once, run anywhere, run everywhere portability in native as well. So we map the JavaScript API into C, and we have this header called webgpu.h. And that C API is shared by multiple implementations. So Dawn, which is Chromium's implementation of WebGPU, and WGPU native, Firefox's implementation of WebGPU, and Emscripten, which compiles C and C++ to WebAssembly, all implement this header. They're not all quite interoperable yet, but they will be by the time we're reaching 1.0 on the spec. And this makes it really easy for applications to port to WebGPU. So if you have a native application in C or C++, you don't have to build your whole thing to the web and then sort of like try to write your WebGPU backend inside of that build. You can do it in native first, and then you can just retarget it fairly effortlessly. All right, so I'll just give a quick live demo. So here's a couple of cool demos from my coworker, Brandon Jones, Toji on GitHub. He's built a couple of really cool demos showing off some of the capabilities of WebGPU. So this one is a clustered forward shading demo. This is using compute shaders to optimize a lighting situation where you have many, many lights. So here I have the lights. I have 240 lights. I'm getting about 60 frames per second. If you compare this with a naive forward implementation, then let's see, that goes about 30, 40 frames per second. And as you crank up the light count, that distinction becomes really big. So here, 15 frames per second in naive, and a good 22 with clustered forward. I think usually this is a little bit faster. Probably the difference is smaller because I made the window really tiny. And then here's another demo that he put together. So this one is just doing some metaballs. So we've got a bunch of particles. We've got a particle system here, and he's meshing it out into a solid geometry and doing dynamic lighting using it. All right. So now I'm going to go into a bit of background about why we are building explicit APIs. So all of the native APIs have gone in this direction, and now the web is too. And I'll just give a few examples. There's many reasons, and it would take many hours to go into the details about them. But I'm just going to give a few examples of things, design changes in the explicit APIs that make a real difference. So explicit APIs get closer to current GPU architectures. We get better support for tiled architectures. We get pipeline state objects for pre-compilation. And of course, we get to leave behind the legacy design of, say, of OpenGL, which dates back, the design of which dates back all the way to the 1980s with IrisGL. So now we have an object-oriented API, which means no more hidden global GL state. None of this bind this, and then when you bind this other thing, it applies to the currently bound other thing. And also no more last moment compilation and validation. So our draw calls are very light. We no longer have, thousands of lines of checking dirty bits to make sure that we've updated all of the state correctly during a draw call, which, draw calls are supposed to be fast, right? You want to do 1 million of them. And all this comes together to give us a much stronger foundation for new features. So to talk about the multi-threading, single-threaded APIs like OpenGL have historically had this issue where all of the graphics work has to be issued from a single thread. And this is sort of because of this global shared state. Since there's global state, it doesn't really make sense to try to manage it from multiple threads at the same time. So engines would end up putting all of their graphics work on one thread, or almost all of it, and then offloading just everything else that they possibly can to other threads. So say an audio thread and a physics thread, for example. With multi-threaded APIs, you can distribute this graphics workload across cores, which gains some serious both power and performance improvements. Another reason is predictable behavior and performance. So with the designs of the new APIs, of the explicit APIs, applications can control when expensive operations happen, like pipeline compilations especially, rather than having them happen implicitly inside of draw calls, for example. This gives you much lower frame variance between frames, which is really useful for VR and a lot of other applications. And generally, the application has a bit more control over when, say, it does pipeline compilations. And it can be smarter than the OpenGL driver because it knows what it's going to do in the future, whereas the OpenGL driver only sees what you've done in the past. As a quick example of something that seems simple in OpenGL, but really is not, in OpenGL, the user wants to resize texture. Okay, they call text image 2D, that should resize. And in the future, if they use it again in the future, then they see the resized texture. In practice, though, the driver has to do more than that. So it doesn't just have to allocate and use new memory. There could also be, operations in flight already. So the application or the driver might have to insert a fence and then periodically check that fence to make sure to see whether the old allocation is done being used, and then it can garbage collect it. And then on top of that, all that internal state means that a whole bunch of things need to be rebound to the new allocation. So any shader uniforms, frame buffers, texture buffers, all these things could be pointing directly at the old allocation. So we have to go find all of them and mark them as dirty so that later on we can update them. During the draw call, we can update them and say, okay, this is pointing at the new texture. Now I'll talk about pipeline state objects. So in the OpenGL view of things, we see the pipeline as a bunch of individual pieces of state. So we have use program, depth func, like all the depth testing and depth right state, blending state, frame buffer write state, and a bunch of other stuff. And the actual GPU, on the other hand, might be viewing these in larger chunks. So for example, the actual GPU might take your depth testing configuration and fold it into the fragment shader so that here it injects this if GL frag depth is less than the previous depth, the old depth, then discard the fragment. It might fold the blending into the shader as well. And so every time any of this state changes, it's going to need to rebuild. It's going to need to regenerate and recompile that shader. So in the explicit APIs, we see all of this stuff bundled together into a single thing called the pipeline state object. And we build that ahead of time. And then with a single call, we set the entire pipeline. And the driver doesn't have to do any lazy compilation or anything like that because it's already gotten all the information it needs ahead of time. Next, I'll talk about command buffers. So I'll just quickly, this one's pretty simple. The basic idea of command buffers is that you serialize commands like draw and set pipeline, et cetera, into a buffer, into some sequence of operations. And then you can send the entire batch with a single call. There's no state tracking between command buffers. All the state is inside the command buffer, which makes these nicely encapsulated. This gets us multi-threading because we can encode multiple command buffers on different threads at the same time. They're totally independent. And then put them all into the queue for the GPU to execute. And that's it, right? There's no trying to deal with like shuffling things around between threads or like terribly complicated synchronization. Now I'll talk about render passes, which are a really important subcomponent of command buffers. I'm going to go through this really quick. It's pretty complicated, but the typical way that we think of rendering is that we've got a bunch of triangles that we want to render. And for each triangle, we want to break it up we want to rasterize it, break it up into pixels, and then write those pixels into the frame buffer. The problem with this is that when you do it this way, you're effectively doing random access to the frame buffer memory. You end up loading the same pixel from the frame buffer many times and storing it back. And so you thrash the caches and you do tons of frame buffer reads and writes between the execution unit and the memory that holds the frame buffer. This is really expensive, especially in mobile. The bandwidth costs a lot of power and it slows things down. So the idea of tile-based rendering is to sort of flip the loops and say for each fragment in the frame buffer, we're going to render all the triangles that intersect with it. That way we only have to load the value from the frame buffer once, render all the triangles that overlap with it, and then write the frame buffer data out. That reduces the number of writes, but storing triangles for every pixel is a little expensive. That would be like the number of pixels times the number of triangles. So in tile-based rendering, we split this up into tiles. And then for each tile, we do this operation, say a 16 by 16 square. We load the whole square in, render all the triangles, and then load the square, and then store the square out. What this looks like is, with an example, here's a couple of triangles that we want to render. We'll take one triangle, split it up into parts for each of the tiles, and put those into the buckets for each tile. And we'll do that for all the triangles. And then when we want to render one tile, we'll take each triangle and render it into that tile. And then we can store that entire tile out to the frame buffer memory all at once. And then we can do that, repeat over that for all of the tiles, potentially in parallel. there's a bunch of more optimizations that you can get from render passes. So it's not just for tiling architectures. So for example, what if the initial depth is a constant 1.0 or the initial color is a constant black? Typically, you don't necessarily care about the current, you don't always care about the current contents of the frame buffer. So instead of actually loading those out of memory, we can just say, this is a constant value, initialize it to that constant value inside the tile, ignore the current contents of the thing. And then sometimes you'll have data inside the frame buffer, like depth data for depth testing, or multi-sample data that's only used for multi-sample resolve. And we don't have to store those to memory either. We can just discard those at the end of the render pass. We only have to store the result that we actually care about. So this saves a lot of bandwidth potentially. So the render pass is basically a subsection of the command buffer. It surrounds all the draw commands, and it just defines the shape of the render targets. And basically for each render target, whether you load it or clear it at the beginning, and whether you store it or discard it at the end. Now I'll go through a WebGPU tutorial. So here's a small application that I put together. It's heavily based on existing demos that we already had. I just put it together as a single file, so it's easy to browse through. So here's the demo. This is doing a pretty simple compute-based particle simulation. So it's doing Boyd's, the classic Boyd's particle simulation. And then it's taking the results of that simulation and rendering it out to the screen, instancing this little spaceship thing, the airplane thing, which is a 3D object, and doing some lighting on it. So it's a pretty straightforward demo, and it doesn't take a lot of code to do this. So the first thing is initialization. So the important difference here with WebGL is that in WebGPU, a device is initialized without a canvas. So in fact, a WebGPU can be a single WebGPU device or context can be used with 0 or 1 or more canvases at once. It's totally decoupled. So the first thing we do is request an adapter that identifies which hardware adapter or implementation we're using on the system. And then from that adapter, we request a device. And that device is sort of a virtual device object that gets to assume it's like, this is a GPU, I'm the only thing running on the GPU. It's effectively like a context in WebGL. And then separately, without the device, we also can initialize a context on the canvas. And this is just like a saying, we're going to use this for WebGPU rendering later. And then later on, dynamically, whenever we want, we can reconfigure the pairing to create a swap chain object. So we take a context and a device, and that gives us an object that will give us a new render target texture every frame. And that texture that it gives us is just going to be a regular texture. So we can just use it as if it's a regular texture and draw into it like a render target. So this really simplifies the model of how, like, there's no more default frame buffer. It's really just like frame buffer objects for everything. Next, we'll do the simulation. We'll create a shader module, create a compute pipeline from that, and allocate and initialize some resources. So this is a bunch of code, of course, but here we have a shader module for the simulation. The important part here is the bindings. So here we have a uniform buffer for the parameters and a storage buffer to read from and a storage buffer to write to. So we'll be ping-ponging back and forth between 2 storage buffers each frame. And inside here, we just do all that simulation. Mark this as a compute entry point, set the workgroup size and all that. Creating the compute pipeline is really straightforward. It's just providing the shader module and providing an entry point, specifying which entry point in the shader module we'll use. Next, we'll initialize some resources. So that uniform buffer that has all the simulation parameters, it's pretty straightforward. We just create a buffer. We marked it as mapped at creation, which means that when it's created, we can start writing into it. So we get an array buffer from that, which gives us a writable array buffer that lets us write into the buffer, set some data into it, and then unmap it. And now those are the initial contents of the buffer. And then we can do the same thing for the initial particle position and velocity data, which in the demo, we just randomized. And then we create a couple of bind groups. So we'll create one bind group. We'll create two bind groups. For this, we'll create one for going from particle buffer 0 to 1, and then another one for going from 1 to 0. So we can do that ping pong. We can switch between the two bind groups every frame. Next, we'll talk about rendering. So create a shader module and create a render pipeline from it. And then just allocate and initialize the render targets. So again, create a shader module. Here you'll notice that there are two entry points inside of this one shader module. We have the vertex shader here and the fragment shader here. And they're actually sharing an interface. So this structure, which I've called varying, which is similar to the WebGL concept, we share this structure between the output of the vertex shader and the input of the fragment shader. So you can see that, so you can reuse this code to define the interface point. And in there, we have some very basic data for rendering. So to create a render pipeline, there's a lot of data that goes in here. The first thing is the vertex buffers. Use the concepts are the same as usual. Here we're setting it up as an array of structs for the particle position and particle velocities. We specify the render Boyd's vertex entry point in the shader module. We specify the primitive topology triangle list. Set up some of the depth stencil state. So we're enabling depth right, and we're enabling depth testing and setting the depth compare function. Specifying how many samples the pipeline will render. And then attaching the fragment shader and specifying the format and the number and format of render attachments that the fragment shader will write into. And there's a lot more stuff that can be specified in a render pipeline as well, like blend state and that kind of thing. That's not shown here because they all have default values. So we'll initialize some scratch space for rendering. First, a multi-sampled color texture. We mark that as a render attachment so that we can render into it later. We give it 4 samples. That's pretty straightforward. And we do the same thing for a depth texture, create it with a depth format and do the same thing. Now we can configure those two things together into a render pass. So here we have a list of color attachments. So for each color attachment, we specify the view, which the attachment data will be stored into, and then a load value for the beginning of the render pass. So here we're doing that optimization. We specify a constant color. We don't care about the current contents of this frame buffer. We load a constant value, and at the end we discard the data. So we say clear at the end so that it doesn't need to store any data. And then here in the middle, this part is important. We have the resolve target, which we'll fill in later with the canvas texture. So the canvas texture is always single sampled, but we want to do multi-sampled rendering. So rather than storing the multi-sampled results out to memory and then having some resolve step to resolve them into the canvas, instead we do it all inside the render pass. So at the end of the render pass, we can throw away the multi-sampled data because we don't need it anymore, because it's already been resolved directly into the canvas texture, into that single sampled final result. And then same deal for the depth stencil attachment. We don't care about the old data, so we set it to a constant value of 1. And we don't need the data at the end, so we discard the scratch data at the end. So we can just put all that together. Each frame, create a command encoder, encode a compute pass, encode a render pass, and then finish and submit that command buffer to the GPU. So this is pretty straightforward as well. We just create a command encoder object, and then we start recording into it. For the simulation, we begin a compute pass, and then just set a pipeline. We've already set up the pipeline. Set a bind group. We've already set up a bind group, and issue our dispatch call of the appropriate size. And that just does that read from the source buffer and writes into the destination buffer and does one step of the simulation. And then we end the pass. Next, we can go to the render pass. So here we update that resolve target that changes every frame. So we grab the current texture from the swap chain and attach that as the resolve target of the render pass. And then we simply encode a pass encoder. It looks exactly the same. We set a pipeline, we set a vertex buffer, and we issue a draw call, and that's the whole pass. Here you'll see that it's 6 vertices for each of those little spaceships, and then it's instanced over the number of them. So this is doing instance rendering. And at the end, we just finish the command buffer, finish the command encoder, which gives us a command buffer object, and we can submit that to the GPU to execute. So I'll just go back to that. I will now show the same exact demo running in Firefox. All right, here we go. So here's the demo running again in Firefox. So this is the same code. It's fairly basic usage of the API, but a lot of demos are able to run in both Chrome and Firefox. And both are very, very, very close to the top of the to the latest specification. So both are very much in active development. So I'll just go back to the slides, and will be about it for me. Sorry that I've gone slightly long. So to get you started with WebGPU, here's a bunch of resources. So first of all, the W3C GPU for the Web Community Group. We've been working on WebGPU in that group for about 4.5 years now, I think. You can find it on the w3.org website. The participants are Apple, Google, Microsoft, Mozilla, a bunch of other companies, a bunch of individual contributors, and it's open to the public, so anybody who wants to join can join. So please try out WebGPU, report any shortfalls, any issues that you find with the design, or issues that you find with the browsers, and join the discussion. You can find the specification on GitHub, the specification repository on GitHub, and you can go to these URLs to view the WebGPU specification, the WebGL, the WGSL WGL specification, and an explainer that talks about a lot of the design details of WebGPU. Additionally, there are tons of resources, not that many actually. There are a few resources out there for WebGPU right now. So we have the WebGPU samples, which is maintained by my coworker Austin. The clustered forward shading demo that I showed, the MetaBalls demo that I showed, and then a couple of other useful examples for native and WebAssembly. There's blog posts and tools like 3JS and Babylon.js are getting WebGPU backends. So if those are tools that you use, you can try those out as well. And in this talk, I've used TypeScript to make it clear what the types of all these objects are. We have a TypeScript type definition file that's used by a lot of projects, and including TensorFlow.js, the test suite for WebGPU, and a lot of community projects. So thank you all for listening. I just want to quickly acknowledge the efforts of the W3C community group, my co-editors, Dimitri and Brandon, all of the contributors from all of the companies and individuals contributors that have helped out with WebGPU, the WGPU RS community, which is very active, the Dawn community. A lot of the slides that I showed here were adapted from my coworkers, Quentin Varese and Austin Eng. And of course, a big thanks to the Khronos Group for hosting WebGPU at this meetup. Since WebGPU is not a Khronos standard, this is a Khronos meetup. So it's really gracious of them to allow us to share this space. Please post your questions in Zoom, and I'll hand it over to the next presenter now.
That was awesome. Thank you so much for running us through that. I know I'm not the only one who got a really nice feeling off of and better understanding from what's going on with WebGPU. So exciting. So up next we have Marcus, who's awesome. Looks like you're ready to go, sir. So whenever you're ready.
Yeah, hey everyone, thanks for joining today. I'm going to talk a bit about our experiences of porting Poetry to WebGPU. So Poetry is a WebGL-based renderer for large point clouds. It can be used to render tens of billions of points in real time in web browsers. The one below here, for example, it has 18 billion points. That's about 200 gigabytes compressed, and it runs in real time in web browsers today. The level of detail structure that we're using for that is some form of octree, where each octree node contains about 1,000 to 20,000 points. And there's some kind of point budget that users can change, which then tells us how many nodes, how many points should we render in each frame. That number is usually about 1 million to 10 million points, which corresponds to around 100 to 4,000 nodes. So what I'm going to talk about today briefly is two topics actually that were very interesting for Poetry. One is depth buffer precision in WebGPU, and another one is compute data rasterization. So depth buffer precision has always been a bit of a problem because Poetry is used to render very large data sets, as in data sets with an extent of tens to hundreds of kilometers. And at the same time, it can be that there are objects very close. So we have a very large depth range, and this has always been a bit of a problem. It's especially a problem in two cases in our experience here in Poetry. One is virtual reality rendering. So when we integrated virtual reality, the problem was that we had controllers that are close to the viewer. And at the same time, we had point clouds with 100 kilometers of size. So the near clip plane had to be very close, the far clip plane had to be very far. And in the end, we didn't have a good quality in virtual reality. There are some potential workarounds, but they're tough to implement, and they usually have some kind of performance issues. Another thing where this was a bit of a problem is for item lighting. Item lighting is a shader that's often used for point clouds because many point clouds, they don't have normals. So in order to compute some form of shading, we use the depth buffer to analyze the neighborhood. And it's basically some kind of edge detection filter. If there's a lot of difference in the depth, then we do some other shading values than if there's none. Now the problem was, as you can see to the bottom right here, that if the depth buffer precision is insufficient, we end up with something like this here, where lots of depth values get rounded to the same value. Those are the white regions. And then we have sudden steps where the depth buffer value changes. But it's supposed to look like the two images to the left here, where you can see there's some nice shading going on, just computed from the depth buffer. Yeah, in order to do that in WebGL, we used some workaround where we stored a high precision depth buffer value in logarithmic depth buffer value in a floating point texture, but that was some additional work to do and with some performance issues. With WebGPU, it's no longer necessary because it supports reverse C. What that means is that we can map the near clip plane to the value 1 and the far clip plane to the value 0. And with floating point values, 0 means that we have a bit of a higher precision. So what happens is that the far clip plane or objects in the distance, they get some more depth precision. It's pretty easy to integrate. There's a reverse C demo in the WebGPU samples repository. And at least for item lighting, it worked very well out of the box. And I guess that it will also work very well for virtual reality, because even the point cloud with 100 kilometer, it works very well now with a near clip plane of 0.1. The one thing that I'm most excited about WebGPU are compute shaders, and because you can do a lot of interesting stuff with that, and for point clouds, they're especially useful because you can use compute shaders to render the point cloud. And unlike with triangle software renderers, it turns out that point cloud software renderers using compute shaders can actually be a lot faster than the native primitives. So typically, you'd use GL points or point lists to render a large amount of points. But those two primitives from the standard rendering pipeline, they scale very poorly to a large amount of points. So when you render hundreds of millions of points, then computers can be about 10 times faster than GL points or point list. The way that this is done is we can simply use atomic min, and the code samples below here, they're from our OpenGL implementation. And what we do here is we first compute the depth value of a point and the RGB coordinate value of a point, and we encode both of these things into a single 64-bit integer. And then we can use atomic min to store the point with the smallest depth value. And afterwards, we can extract a color to store it into a texture. What you can also do is you can extend this with some further performance improvements. For example, you can easily add some kind of LAC test where you first load a previously stored point, and then you compute a new point, and then check if the new point is closer than the old point. If it's not, we don't need to do any atomic min operation here, which are more expensive than simply loading this old point value. So in order to implement the fastest way to restore points with computers, we would need 64-bit atomic mins or atomics. We would also need some subgroup operations, especially shuffle and subgroup partition. Right now, it's looking like that WebGPU won't have the more advanced functionality in the beginning, but we can do some workarounds. For example, instead of 64-bit atomics, we can split this into render passes. So first we render the depth values of the points using atomic min on just writing the depth value. And afterwards we can continue with a color pass. Because some points might end up with the same depth value, it could be that this flickers from frame to frame. So the color best doesn't actually use some kind of atomic min or directly sets the value. What it does is it adds up the values of all points that pass the step test, and then it afterwards another pass computes the average value. Nice thing about that is that that it can be used to not just render the nearest point, it can also be used to compute an average of overlapping points. This is which is especially useful for point clouds because we don't have texture filtering like with textured meshes using bitmaps. So usually we have very high aliasing problems, and this kind of two-pass approach can alleviate this a bit. Yeah, in the future, I've seen that there's a subgroup proposal already going on to extend WebGPU. And in our OpenGL implementation, we already had some great success with these three approaches here. So one thing we can do with subgroup communication is we can check if all threads in the subgroup write to the same pixel. So let's assume that there are 32 threads writing to the same pixel. Then we can check if they all write to the same pixel. And if this is the case, we only let one of those threads actually write to the pixel, so using the atomic min. This works pretty well when zoomed out and when a point cloud is sorted, but it's usually not very likely to happen. So if this here fails, we can also check if pairs of threads write to the same pixel. And so if two threads write to the same pixel, only one of them is going to do the atomic operation, which can cut the amount of atomics down to half. The highest performance was usually achieved with some kind of subgroup partitioned operation, which can reduce the number of atomics to the exact number of affected pixels. So if a subgroup writes to 3 pixels, we're only going to do 3 atomic operations. The last one here is probably a bit very recent, and I think also vendor specific, so it might not appear in WebGPU anytime soon. But the first one is already in a proposal. The second one, I've heard there might be a workaround that works. So I'm very optimistic that this is going to work out very well soon. But yeah, this two-pass approach, I've already implemented this in WebGL, in WebGPU. And here are some of the results. So this is the same point cloud with 140 million points. And in a close-up view, point list renders this at about 66 frames per second. With the compute-based approach, we already have a high frame rate at 80 frames per second. And an interesting thing is when you zoom out very far, then point list drops down to 7 frames per second. But the compute shader approach still are pretty fast with almost 70 frames per second. And also the The one subgroup functionality that I mentioned that is the fastest one, in our OpenGL implementation, this one actually made it so that the viewpoint doesn't matter at all. So it was always same speed, always peak performance. So maybe this is coming to WebGPU at some point in the future. Yeah, also there's a limitation for that. It only works really well if you have a large amount of points in a vertex buffer, so about 1 million. This is not yet the case for the LOD structure in Poetry, which has about 1,000 to 10,000 in a vertex buffer. So it's not yet useful for LOD rendering, but it's already very useful for rendering a large amount of points, very large point cloud models without LOD. But regarding LOD performance, so simply porting the current WebGL version to WebGPU, we found speed ups of about 3 times faster in WebGPU. Might be multiple reasons for that. Maybe better decisions this time around. Maybe WebGPU don't know about that, but generally it looks like a pretty nice API, and it's working very well for us. So yeah, thank you for attention. And here's some links that might be interesting, including 2 demos.
Awesome. Thank you so much, Marcus. And is there a good way for people to contact you or follow your work?
It's a good question. So there's at the first link here, you will find some kind of data to contact me.
Fantastic. All right. So thank you for that on Poetry. And bringing us home for the final presentation is Ian with Hypar. So Ian, whenever you're ready, sir.
Okay, good morning, everybody. Let me start this off here. Always difficult to follow amazing presentations like that. I mean, Kai, we're certainly going to take advantage of the work that you showed around WebGPU and lighting. It's a very important issue, obviously, in architectural design. And Marcus, the stuff around point clouds is incredible. I'd really love to catch up because obviously point clouds are becoming quintessential to the building trades for how we record the built environment and then we design new things into them. So hello, everybody. My name is Ian Keogh. I'm the CEO of a small software startup called Hypar, based in Culver City, California. And along with my co-founder, Anthony Hauk, we're both ex-Autodesk individuals. We've worked on large projects like Revit. Traditionally, we're in AEC, which is architecture, engineering, and construction. And I'm going to talk just a little bit about our startup Hypar. Let's see if I can advance here. So just a tiny little bit of background. This is like a very, very small PowerPoint presentation, hopefully about 3 slides. And then I'm going to do a kind of a live demo. We'll see how that goes. But just to give you some context, in building, since about the 1970s, people have been imagining how we're going to use computers to generate buildings. So starting even in the 1970s, before we had desktop computers, people were writing punch card programs to lay out types of buildings that are very prescriptive in their design, like hospitals, right? So here's an example from Gerald Delon. And literally in 1970, they were writing computer programs for how to generate buildings. Well, of course, over the years, we went through computer-aided design in 2D and then computer-aided design in 3D. And now what we have is what's called building information modeling, where we try and build like really, really, really high fidelity models of buildings. And this is great. It has brought some efficiency gains to our industry. But the challenge is that all of this, like these complicated mechanical systems, for instance, for a building, like you're seeing on the screen here, built with Revit, are all done by hand. So there's kind of an emergent practice in AEC right now, which we've kind of coined generative design. Generative design distinguishes itself from what came before because we're actually allowing algorithms to design large parts of the building, and we're building sort of augmented design experiences where architects, engineers, contractors can actually reach in and work with the algorithms to generate the things that can be generated, and then to override those with sort of manual design where that's appropriate as well. So it's this kind of hybrid between manual and generative design. So Hypar started in early 2018 to approach this idea not only of generating buildings with computers, but also creating a platform where people could share their expertise as code and build larger and larger sort of aggregated building systems. So we were solving some kind of complicated problems around distributed compute, but also visualization on the web. This is a highly simplified architectural diagram of what we're doing. But basically, Hypar is a web application. It's a single page application implemented in Vue.js, but we use 3 as our framework. So I'll say I'm not an expert in 3D graphics like many of you might be. So we take advantage of all the amazing work that you do, typically through a framework like 3JS, which is a choice that we made in 2018, but we've obviously been investigating other platforms like Babylon and Cesium and others over time to see what they can offer us specifically in AEC. And so the really critical thing about what Hypar is doing is in the back end here, we talk to our API, and our API spins up any number of services which are executed as Lambdas in AWS. So most of our back end is run as functions as a service. And those functions are actually what compute the building systems. And I'll give you a demo of exactly what these functions are in a second. But it's important to understand that each one of these little services in the back end is something that's provided by a member of the community. So you can think of Hypar as kind of like a software that doesn't start with any buttons, and you have to go and like build capability into the software, deploy it, and then it's available in the community and you can start pulling down functions. And again, I'll show you what that means in a second. But these functions on the back end could be things like a function that generates a structural system for a building, or a structural or a mechanical system for a building. You can implement these things in like C#, Python, Grasshopper, which is a language that many of you might not know, but it's a sort of a visual programming language that we use heavily in AEC, and everybody's favorite design language, which is Excel, right? So you can drag and drop these things onto Hypar, turn them into functions. So critical to this conversation, and probably the reason that we're here, is we use some of the technologies that have evolved out of Khronos standards, things like GLTF. So our backend services actually render out the 3D geometry in GLTF. And then we store that and we pull it back down to the web client. And we can do all this stuff sort of in parallel. So I'll show you exactly how this works. But before I jump over to that, I'll give some links. This presentation is actually in the list of presentations that are freely available and are going to be provided by the group who's putting this together. So just to give you, you can go to hypar.io. That's our website. You can sign up for free and try out everything I'm going to show today is totally free, so you can try it out there. A lot of what we do, the core libraries for what we create in our services are open source. So you can go and see the open source frameworks and SDKs that we've created for doing most of what you're going to see today. You can go and get started with some of our docs. We do a bi-weekly live meetup where you can watch us actually develop new services for Hypar, new functions for Hypar that do crazy things like layout offices, build structures, all the kinds of stuff that people in AEC care about. And then you can follow us both on Twitter at HyparAEC and on Discord. So, like I said, it was going to be a short presentation, and we're going to go over and actually look at some running stuff. So, like I said, Hypar is a web application. So everything that you're going to see here can be done on your desktop. It can be done on your mobile. And in fact, later versions of mobile are actually really, really amazing at executing JavaScript. I just bought an iPhone SE, which actually runs Hypar faster than my 3-year-old MacBook does. So there's amazing gains being made there. But if you go into Hypar right now, you create what's called a workflow. So we're going to create a new workflow. And we're actually going to try and generate a building in like the 5 minutes I have left. Let's see if we can do it. So we're going to create a new blank workflow. And we're going to call it our WebGL Meetup. And oftentimes in architecture, what you do is you start with a site. So what I'm showing here, this list here, is actually all of those functions that are available from our community and those things that I showed executing in the back end. So when you create a new function on Hypar, you deploy it to Hypar, and then it's freely available if you make it public to anybody who uses the service. So we have one function that just allows you to pick a location somewhere on the planet Earth. And we use third-party APIs like Mapbox to go and look up location and topographic information and context buildings and the like. And so let's go find like an interesting location to build something. London, England. And I apologize to anybody who might be watching from the UK. I'm just going to build it. I'm just going to zoom in and build somewhere in London. Let's say here. I don't know what's here. I apologize if I build an ugly building like right next to your building. And then I'm going to turn on things like context buildings. And so what this is doing is these services are actually executing on the back end and rendering those GLTFs. And then those GLTFs are loaded into Three.js using the GLTF loader. And I'll actually try, as I'm going through, to point out some of the things that we're doing perhaps in inelegant ways. And you can all ping me afterwards and tell me, hey, there's a better way to do what you're doing. But little tricks, especially around AEC. So for instance, we're rendering with this kind of ambient occlusion, but ambient occlusion isn't great frame rate wise, especially for these large scenes that we're going to render. So we kind of like turn it off when we're manipulating around, and then we turn it back on. And so we could probably do that more effectively, but and then let's add a site for our building. And one thing that you'll notice as I start doing this is that the functions that are over here in our workflow on the left are actually going to execute in parallel where they can, but there are certain dependencies that some of the functions have on other functions, and you'll see those things execute in sequence. So I'm going to go ahead and draw on a site here. And the things that people in AEC need in their sort of visualizations are often like perspectival views, but of course also like orthographic projections, right? We've been drawing an orthographic projection for 500 plus years. And because of the precision and the nature of the things that we do, we have to use orthographic projections sometimes. So I'm just gonna like draw a little site for my building here. And that doesn't do much, but actually what one of the functions does here is it just creates a site object that other downstream functions can hang off of. And of course, here it just renders one little green triangle, which of course, Z-fighting, right? This is like the bane of every 3D programmer's existence ever. But on top of that site, what I'm gonna do is I'm gonna add some grids. And grids are fundamental to the way that we lay out buildings. Hypar allows you to import and export out of a lot of like standard formats like CSVs. So we're going to put in some grids here, and maybe we'll put in some grids going the other way too. And we're going to set a transform for our project, which maybe like, this is all just defining the site sort of layout, right? And then what we're going to do is we're going to go and we're going to define an envelope. This is where stuff starts to get a little bit more interesting. You actually build the envelope. Actually build the envelope for your building, let's say by sketching it. There's a lot of different ways to create an envelope. And we're just going to go back into our ortho view here. We're going to go to the top. And we're going to sketch a shape for our building. Maybe something like that. Now you start to see these functions re-execute as they get their dependencies from other functions. And it's not doing anything like super remarkable, right? It's just like building a cube. So let's go back into perspective for a second. And then it starts to get interesting when you say, I want to add a steel structure to my building. And it tells me, it says, well, according to the dependencies here, the steel structure depends on this thing called bays. Would you like to add some bays? Sure, I'll add some bays. And it also needs some levels too. So I'm going to say simple levels by envelope. Add these. So my grid, along with my levels and my bays, starts to lay out the structure of my building. And here's the structure of my building, right? We can even go and add something like a facade. Now, the cool thing is that because Hypar is a kind of a contributory environment, people can come in here and actually add their own functions. So the next time I show up, there might be a function for generating a different kind of building system in here. We can also add some floors to my building. Floors by levels. Yeah, because I've got some levels in my building. Oh, but it says, you know what? I don't want to do that one. Let's do, yeah, let's add a core. Core by, I don't know what's going to happen. This is going to try and add a structural core to my building as well. But you'll see that every time I add something new, these dependencies are being recalculated. Those services are being spun up in the back end. GLTFs are being generated and those are being streamed back down. Now, one of the cool things about the scalability of this system is that you can do things like generate a whole bunch of options. In design optioneering for architecture, oftentimes you want to generate a lot of options for how something should look and look at different calculated values. So I'm going to go in here and I'm actually going to tell it, I'm going to move my zoom controls out of the way for 1 second. I'm going to tell it, I want to vary the top bottom inset of my glass. So what's it doing? It's actually going off and recalculating a number of options that span across the range for that parameter on that function. And it's calculating all those GLTFs on the back end and then presenting to them to me as various options, which I can click through. And it's a little bit hard to tell with these smaller images, but if I click on one of these, it's actually a different generation of that facade system. And of course, all of those facade systems have different characteristics in terms of their opacity, the visibility through the glass and whatnot. And where things start to get a little bit tricky for us, and we're very close to the end here, where things start to get tricky for us in architecture is larger and larger models, right? So as soon as somebody wants to do something like layout space planning in my building, and then I want to say inside my space plan, I want to use an office layout. Maybe an open office layout. What you'll start to see is that we generate a lot of content really quickly. The cool thing about working in architecture is that we like to joke that a lot of what you're visualizing is flat stuff with holes in it, linear extrusions, sheets of material, and that's all well and good. But when you get into content, you start actually rendering a whole lot of stuff really quickly. So here we take advantage of things like instancing in GLTF, but a lot of the frameworks that we're using don't do, for instance, like GPU instancing yet. So that's something we want to look into around our content story. And if I zoom out for 1 sec, hide some of this stuff, you can start to see we're actually generating this building in real time. And you can take the GLTF right out of here, the composite of all of these functions running. And you can just use that in any other environment where you can use GLTF. So things like real-time simulation, VR and AR are places where we're experimenting. And finally, just like a couple of little things that are things that we know we need to work on are like, you can see the quality of the shadows here as we expand the shadow map over the entirety of the city. But of course, if we go and turn off our location function, we get a lot more precision in the shadow maps because we're clamping it down to the size of the building. So implementing things like cascading shadow maps to improve the visual fidelity of shadows and whatnot are targets for our research as well. So I'm probably at about 10 minutes, but I think we managed to build a building in 10 minutes. And I invite you all, if you have comments and questions in the QA, happy to answer what we're doing here to the extent that I can. And go to hypar.io and try us out. Thank you.
Super awesome, Ian. And the way that folks can get in touch with you, Twitter handle, email.
Yeah, hyparaec on Twitter. And then we also have a link there that's pinned to our Discord channel if you're interested in getting involved, or if you're one of the hyparaec followers that's here following along.
Awesome. Awesome. Great presentations. Our last two presenters showed where we can almost literally have the whole world in our browsers at least. So super, super rad. And now is the time for the questions, the Q&A. So it looks like we have a decent amount of questions here, and we will be going essentially from the ones that were the most upvoted and down. So for the presenters, go ahead and feel free to jump in here for any of these, but we'll start off. Wayne asked, whatever happened to WebGLstats.com? That seemed to be a very popular question, if anyone here has an answer.
Yeah, so I'll take this. The maintainer wasn't able to continue keeping the site up, and we've reached out to him a couple of times to see if we could maybe help him take over it, but sadly he wasn't quite willing to let that happen. So I'll reach out to him again. But basically, unfortunately, that particular statistics site isn't available. For an individual machine, you can still go to webglreports.com, and that queries your capabilities. But I realize that a lot of people are looking for aggregate statistics, and we'll try to consider publishing those from each browser, so that at least you can get some indication of support of various extensions across hardware.
Awesome, awesome. And then the next question we have from Alec is, will it be possible to share WebGPU content across multiple canvases, multiple canvas rendering without brute force copy?
Yeah, actually, I think I already addressed this in the presentation. So WebGPU devices are totally independent of canvas context. So you can use essentially any number of devices with any number of contexts, any number of canvases, and pair those dynamically throughout the lifetime of your application.
Fantastic. Jonathan asks, is there any information or hints as to when Safari's WebGL2 support will be enabled by default?
So as everybody here knows, Apple never pre-announces any plans to ship anything, but the code is all there, and really it would have been there in the iOS 14.5 browser were it not for other extenuating circumstances that I don't even know what they were. So I would expect it to be turned on by default pretty soon. But again, you can turn it on now in the Safari advanced settings. My wife has an iOS 14.4 device. It works there. It's not the absolute latest code, but 14.5 ought to have another more recent browser snapshot that's pretty close to what the top of tree code is. So again, you can try it out now. Please do. If you have a spare device, like an iOS device, please install the betas on it. Test there and file any bugs you see on bugs.webkit.org. We're sharing a lot of code between WebKit's and Chromium's implementation, so you ought to see comparable features and bug lists there. But we really want to make it as rock solid as possible to have really fantastic WebGL2 experience for everybody.
Awesome, thank you. And then our next question, which it looks like that's more of a Khronos question. So we'll let Lisa or one of those folks answer that directly. The next WebGL question.
Actually, that's for me, sorry.
Oh.
Yeah, that was on a Chromium issue that the person saw that. Basically, these are customers who are, for example, paying Google for Google Workspace licenses. And we have to prioritize those feature and, bug feature requests and bug reports. So I'm sorry that, it's taken us 6 weeks or more to triage some of these incoming WebGL issues. Please bear with us. We have a surprisingly small team for the reach of the browser. And we're trying to let most of the team focus on WebGPU. So the WebGL support, we're trying. We'll try to get there. But the best thing for customers to do is to try to find workarounds for these issues, and then tell us, okay, here's how we worked around it, and could you please address this performance issue in a future release?
Awesome. Everybody at Google's not working on this stuff. Come on, Ken. What's going on over there?
So I've been answering some of the questions in text, but I do want to address them out loud as well.
Yeah.
So if you could switch to the answered tab and grab some of the ones that were answered in text but not answered live, that would be good.
Sure.
And I can just grab one. So the top one
was
from Alistair. Since WebGPU works natively, is it a competitor to Vulkan? So slightly, yes. But we think the target audiences for native applications are very different. So of course, WebGPU Vulkan won't be available on the web. So on the web, you'll have to use WebGPU. But in native, we think the target audiences are very different. So using Vulkan takes a huge engineering investment from the software that wants to use it. And not everyone has that. Not everyone can do that. And you might be able to get a bit of extra performance from using Vulkan, but WebGPU is much more accessible, right? So the difference between that simple application that I showed in WebGPU. And an equivalent Vulkan application is probably something like 5 times the amount of code or more to be able to implement that in Vulkan, and that's not even considering the shader tooling that's required. So it's a lot more accessible, and it also is more appropriate if you want to target a lot of different devices without a lot of porting pain.
Awesome. Kai, do you want to grab another one from the one that you answered?
Yeah, sure, I'll do that.
Yeah, sure.
So yeah, a big question is I didn't mention anything about Safari's implementation status in the presentation. So Safari is, the WebKit team actively participates in the design, and the implementations between Chrome, Firefox, and Safari will be fully interoperable. The reason I didn't mention it is just because they don't have a fully up-to-date implementation right now, so it's not possible to run most of the demos in Firefox in Safari. But all of the browsers will support WGSL and only WGSL.
Okay. And then going back to our open questions regarding WebGL and WebGPU, what is the story in debugging tools? Are we still stuck with Spectre.js or trying to split our code from browser-run rendering on native tooling?
Yeah, this was actually a top question. A number of people asked related questions previously.
Mm-hmm.
So we haven't spent a whole lot of time on our debugging story right now because we still have a lot of work to do just to be able to ship the thing. But there is we have been doing some debugging with native tools. So for example, when you're on Windows, WebGPU typically will be using Directory 12. You can use Microsoft's Pix tool, and you can attach that to the browser process, or you can attach it to your native application that's using Dawn or WGPU, and you can use that to debug the D3D calls that are being issued by WebGPU. And a lot of the time, this will give you really useful information, even though it's not exactly the same API. It is closer to what the hardware is actually executing, so it can be somewhat easier to debug sometimes. Of course, it's kind of a process to hook up Pix to a browser. Unfortunately, I don't think we have any great documentation about that. There's a little bit of documentation on how to hook Chromium up to NVIDIA Insight for debugging WebGL and things like that. But our tentative plan, I think, is that we need to make all our error messages better because they're all bad right now in Chrome. We need to have a few more nice features just so developers can see what's going on. But when it comes to really low-level profiling and debugging, for now we'll be relying on the native tools because it's very hard to build portable tools that could be shipped in the browser, for example.
All right. Perfect. And then we're going to jump down. This is a Hypar question. So Ian, does Hypar, whoa. Okay, it looks like I just lost the question.
No, I'm sorry, Damon.
You answered that right as I was probably calling on you.
Yeah, the question was from Mayor. Thank you very much, Mayor, for the question. It was about whether Hypar has a way to filter out functions that aren't executing the way you think, essentially debugging. This is the problem in sort of visual programming in general. And my answer to him was, we have great debugging and feedback information that comes through the function live while it's running. So you can hopefully see what's going on. But we can always do better there. The good news is that Hypar enables you to select from any number of functions that fulfill the same sort of data contract. So it's possible that if one function for generating a certain system doesn't work, you can go out and see another implementation of a function that generates a similar kind of system and drop it in there in place if one of the functions is broken for some reason. But absolutely giving you visibility into debug information and making it easy to figure out what broke in your workflow is something that's critical to us.
Awesome. Thanks for that. And then jumping back to looks like a WebGL WebGPU question. Could it be possible or even make sense to keep using WebGL for rendering with existing engines while using WebGPU at the same time just for compute shaders? Let's say for physics or so. Could they live together on the same page?
All right, this is a great question that we've also gotten many times. Unfortunately, this is quite a difficult proposition. The difficulty is that the two APIs are very much decoupled. We don't have a lot of interop between them. So we are able to do some sort of basic sharing between them. So for example, if you, not yet, we haven't implemented this yet, but if you render into a canvas, then you should be able to import that canvas into another API. So if you render into WebGPU canvas, you could import that canvas into WebGL. However, that's not really the best way to get data between the two APIs. Right now, the only answer we have to this is that you can copy the data down to the CPU and upload it back. Interoperability between the two, like closer interoperability between the two, is not a big priority for us because one, we have so much work to do. There's a lot of major requests, but what we're kind of hoping for is that the community will start building out some tools for doing some, for example, running WebGL on top of WebGPU. And that way you can take an existing WebGL application, put it on top of WebGPU, and then you can start adding WebGPU code. But no one really knows what this would look like yet. So it's a sort of an open research problem.
Awesome. A lot of area for experimentation there. Yes, Ken.
Yeah, let me just toss in one more aspect. So the Angle project, which implements OpenGL ES, the mobile subset of OpenGL on top of other native APIs, it would be technically possible to write a WebGPU.h backend for that library. Okay, so that you would have basically an OpenGL ES implementation, which is WebGL2 compatible, hosted on top of the primitives that are in WebGPU. Then you could conceive of compiling the entire Angle library using WebAssembly and putting that up in the browser in the application, and thereby have an application level shim that would give you full WebGL compatibility on top of the existing WebGPU implementation. So if that hasn't blown your mind, then I'm not sure what will today.
And in fact, you could also get potentially OpenGL ES 3.1, which has compute on top of WebGPU, going that route.
Awesome. So to our final questions, how will the overhead with JavaScript and browser be circumvented for performance?
Yeah, so Brandon gave a great answer about this. WebGPU's API design tries to push most of the expensive work earlier so that a lot of stuff can be done ahead of time. But the issue of JavaScript call overhead still remains. So for example, we're still doing a whole JavaScript binding call for every draw call, for example. This is a problem that's not really unique to WebGL or WebGPU, right? This is just a performance problem with bindings. So in Chrome, in V8, we've actually been working on our teammates in V8 and my teammate Austin have been working on optimizing the bindings calls in V8. So for calls like draw, like WebGPU draw call, which is just a couple of numbers, that's relatively easy to optimize because we don't need to have as much back and forth between the virtual machine and the C++ code that implements it. So, but of course, the implementation of this is very complicated because we have to make V8 understand how to do these calls in a faster way. So we've got a project going on. We're seeing some really nice performance improvements. They're going to apply to both WebGL and WebGPU. And so over time, more and more of these calls should get optimized and existing applications should just get faster.
Awesome. And then last question, what's the advantage of WebGPU compute shaders for Boyd simulation over WebGL2 transform feedback? Yeah,
so for the example I showed, Brandon again gave a really good answer here. So compute shaders are not strictly necessary for a simple compute example like the Boyd's example. But compute shaders generally are a lot more flexible. There's a lot more capabilities that we can expose to them. There's a lot more things that you can do with them, things like subgroup operations and all sorts of other features. that let you optimize a lot of things like, say, matrix multiplication can be done for machine learning, can be done a lot better with compute, wouldn't work with transform feedback. And on top of that, transform feedback implementations. Transform feedback is a very complicated API. It has a lot of weird internal state driver implementations of transform feedback, somewhat vary in quality. But compute is very well supported by all of the APIs, and so we expect it to just generally work better in addition to being more fully featured. There's actually a couple more questions as well that I wanted to answer that are in the answer questions, so we can get to those in a minute.
Yeah, could I just toss in one more thing?
Yeah, go ahead.
So regarding transform feedback, you ought to be able to, in WebGL2 today, get some reasonable and reasonably portable behavior out of it. But an essential difference between it and compute shaders is that the transform feedback, it's running a vertex shader over a big buffer, and the inputs and outputs are mapped 1-to-1. So if you have a fairly simple or straightforward transformation that really doesn't involve a lot of neighborhood about the source data, so like this particular point receives influences from surrounding ones, that doesn't really map very well to the transform feedback model. Okay. But if it's really a very independent, particle simulation sort of thing where the particles don't look at the surrounding ones, then you can make it work. And there are plenty of examples of doing, say, GPU particles in WebGL that are really fast, look really good, and you can get good results out of them, especially if they're more or less stateless, although you can do ping-ponging back and forth. Brandon and several of us contributed to a WebGL2 particles demo a few years ago that that shows actually influences of the mouse pointer over a particle cloud, and you can make that work fairly well. So I would encourage you, if you need to ship the stuff today, investigate using transform feedback, and also at the same time investigate WebGPU and compute shaders, and try to extend your algorithms toward what's going to be the future of graphics on the web.
All right, I'm going to grab a couple of questions that I answered in text. So there were several questions about WGL. So the first one is, I've already got a whole bunch of GLSL shaders in my WebGL application or in my OpenGL application. How am I going to get all of those to run on WebGPU since it doesn't accept GLSL? We're working on tooling to do a robust conversion of shaders between languages. So there's existing tooling like GLSlang for going from GLSL into SPIR-V. The Tint project, which is part of Dawn, which is part of Chrome's implementation, can take in SPIR-V input and output WGL. So that's a path that we're working on. So one possibility is to hook those two together and go from GLSL to SPIR-V to WGL. Another really interesting project is the GFX-RS subproject Naga, which is a general shader translator going from many languages to many languages eventually. And they want to be able to go directly from GLSL into WGL or from HLSL into WGL. And I also expect that Naga would be a much lighter weight thing to ship than GLSlang plus Tint, which is like a pretty big, combined is a pretty big C++ code base. So check out some of that tooling. The story today is like not really well defined. We don't have like nicely packaged up packages for doing these conversions yet. Plus there's a lot of extra complexity that comes from the binding model differing. So you'll have to adjust your shaders for the difference in how resources are bound to the shaders and how like maybe the outputs work. So that's it's a pretty complicated space, but there will be tools to do this. Another question was about several other questions were about obfuscating and minifying shader code, especially if it's proprietary. We don't have any solutions for this today, but the WGL grammar is very well defined. So it should be relatively easy to make a robust library that will take WGL code in, parse it, and replace, for example, replace all the variable names, remove all the white space, things like that. it probably would be pretty easy to adapt the existing tooling, Tint and Naga, to do things like that, but you could also just do it by implementing the grammar. I'll warn you that the grammar today is not really anywhere near finalized yet, so don't go writing this now and expecting it to keep working forever. But I think that this will be a solvable problem as WebGL starts to stabilize more. And I think there was one more thing, a couple more things.
For one more question, it looks like.
Yeah. So there was a question about non-deterministic results when you're reading and writing from storage. So yes, this is an issue. So compute shaders and fragment shaders can read and write from storage buffers, and they can have races between different threads in the same compute invocation. This results in effectively undefined results. The guarantee that we give in WebGPU is that you won't get results from other contexts. So you won't get secure data, like you won't get data that exposes data from another domain, for example. But we can't make this fully portable. We can't make this work perfectly the same on every machine because it's fundamentally very difficult to paper over.
Awesome. All right. Well, and with that, we bring to a close this WebGL meetup. Thank you again, Ken, Kai, Ian, Marcus, and of course, the folks over at Khronos for making this possible. And of course, thank you all for joining us. Don't forget that this presentation and recordings will be online at the Khronos website. And if you are working on a project, as Ken kind of mentioned earlier, if you're working on a project, please make sure to share it with us. We'd love to have more people sharing their work and whatnot. So just make sure to reach out to us either through the WebGL Meetup groups for San Francisco or Silicon Valley, or to the folks over at Khronos. So with that, thank you, everyone. Have a lovely rest of your week and weekend. Keep working on your WebGL stuff. Start working on WebGPU, and we'll see you next time. Thank you. Thanks all.